A very good morning to all of you, all the participants present over here. So hope you had a wonderful session yesterday. So now we are going to start our today's first sessions and the third lecture of this particular event. And as you can see, the title current like the ADME properties and medicinal chemistry. And it's again my privilege to welcome Professor Stark to start and talk about these particular sessions. So please, Professor Stark, it's all about you.
Thank you very much for the kind introduction. And also a warm welcome from my side. Yesterday we've learned that different neurotransmitters are quite important, and you see here that norepinephrine, serotonin, and dopamine, they do have different effects on your behavior and so on. And at the end, you need all of these three medications, three hormones for your motivation at the end. Yeah? And motivation is not only being enthusiastic, it's also being impulsive, having the correct mood for this, having the drive for this. So with different aspects you go then for your motivation in the different aspects. What I'm telling you today is about the ADME properties, or LATME or LATMET really, which is the abbreviation for liberation, adsorption, distribution, metabolism, elimination, and toxicology. So there, mostly all of these pharmacokinetic problems we are working on in this way. Also for my reference, I took a lot of these slides where I'm using today from this small booklet from Cyprotex, which can be easily downloaded after registration. And then you can get more insight and also the references for this for the different structures and so on. And that's mostly focused on the ADMET, what you need as a medicine chemist, and what is needed also for the understanding of the different topics in the different pathways and so on. We started yesterday already with the separation of the drug-body interaction with the pharmacodynamics, and then today we will go to the body-drug interaction for the pharmacokinetics, and we'll there go into further details with the different aspects. I must say it is in many cases misunderstood or only slowly taken into aspects the pharmacokinetic structures, because when you develop new compounds, you investigate the corresponding pharmacodynamics mostly. And then maybe you have a good active drug in your screening system, but you're not investigating really in which way this really has property to go into market or to go into animals to be a chemical probe for different aspects and so on, if it can be applied perorally or it must be interperitoneally applied. And then there are different possibilities in which way this can be considered or must be considered. In fact, when you want to be successful with these strategies, then you have to take this in the drug design into account at the very first beginning for the different structure, and to see in which way this is then going on with the different aspects for the thing. So this LATME property is really important for the investigation of the different structures. So here you see another slide for this. For absorption, distribution, and excretion, and this pharmacokinetic is more or less taking the drug concentration in different tissues, taking the metabolite formation, and also investigating the metabolite activity and the metabolite drug concentration for the different aspects. So absorption, then it goes into distribution into different areas, it goes into metabolism, and it goes into excretion with the different structures. The underestimation of aspects is these are quite expensive to investigate because most of these structures need for a thorough inspection animal studies. And a few of them can be studied by some preliminary in vitro studies on cells or on microsomes and so on, but there you get a good approach and you get a much better characterization of your drug likeliness of your compound or your compound class. So that's the major issue we are talking about. The reason why these things are really investigated, you see here that this is the reason why compounds got attrition in this way. And you see that here the main reason was pharmacokinetics, and this goes down in the year 2000 because the pharmacokinetics is much more introduced in the drug development as it had been before. So the failure of a drug development is strongly reduced the more aspects you introduce at the very first development. Then attrition rate in these aspects. Okay? Not okay? Could be optimized. And you see that here, once more, the toxicity rises again, but this rise is relatively because this toxicity is not always be considered or cannot always be considered in all aspects. And with the reduction of the PK dropout, then the toxicity really would be the other reason why these things are really. So drug likeness for this, and the drug likeliness means that they have the desired pharmacological effects, that they are able to reach the target on site. So from time to time, I have some cooperation partners who want to develop drug for the CNS. And these drugs for the CNS, then they introduce, for example, guanidine compounds. Guanidine compounds are highly polar, highly basic, so they are protonated, and they are poorly passing the blood-brain barrier. So from the screening, they have good compounds. From the toxicology, they have good compounds, but they would not pass the blood-brain barrier, this compound, and do not reach the target. So their drug likeliness is not really good for this kind of aspects you're going for. Yeah? And we need some target selectivity for the pharmacological action, and then the pharmaceutical properties for purity and so on must also needed for drug likeliness. So there are also many aspects for drug likeliness that can be approached. And here you see the ADME in the classical approach, where you had some compound libraries, make some screening, make some lead identification and some optimization, and then you optimize the ADME properties with new compounds, then you go into toxicity, and then you go for your drug candidate. This is a classical way which took a very long time and had a large dropout rate because of toxicity finding at a very late stage, and also the pharmacokinetic properties determined at a very large stage. Nowadays, the people are going a different way. They screen the libraries they have hit, but then they made some early ADME toxicology profiling with the structures. If they do not fulfill all the criteria, then you have to go back to make new lead structure, finding new structural variations, and so on. So this here, they are connected to the ADME toxicity, and the early ADME toxicity must then always be connected to cheap screening, to fast screening, and to efficient readout in this way. That's also impossible, or very important, that you need a good readout and then come to a drug candidate in this pathway here for this different structures. So we go here step by step. We do not handle the liberation, which is also an important point. Liberation means when you take your tablet, then your tablet had to be dissolved, and then the dissolved drug would be absorbed. So this is a more or less pharmaceutical technology problem in which way you go into liberation for the different structures. Here we go for the absorption, and you go for most of the compounds, we have a per-oral absorption. So we go to the stomach in the gut, and then we go to the gut wall, to the portal vein, to the liver, and then we have the liberation or the distribution in the whole body through the circulation. What you also do have and can clearly see that the gut wall, the portal vein, and especially the liver, they are already some chemical compartment and also an enzymatic compartment, and they can have really large reduction of the drug concentration because of the enzymatic and hydrolytic capacity in this area. And this leads to a so-called first pass effect, that the absorbed effect is strongly reduced, and we have the effective dose is reduced for the first pass effect for the different compounds. So if your compound is biolabel and get easy metabolized, then it would not reach the full compartment due to this first pass effect in this way. So make your compound stable enough, low first pass effect, and then we can easily go for this. But you can also surpass the first pass effect with IV application or some other parenteral application form. It's clearly possible to go for a parenteral application or IP application, then you go for the different ways. I cannot explain all of the different absorption pathways because there are also inhalation, the different parenteral application, or if you got some anal applications there are different forms in which way the absorption can then be modified by different forms or by different ways. Even topical dermal application could be a systematic application if you go for transdermal applications and so on. So there are many possibilities in which way this absorption can be arranged and can be modified. So even when your drug shows maybe poor I think the 1, 2, 3, yeah. With the per-oral absorption, then you can change this to transdermal absorption by a patch or something like this. So there are different ways in which way this can be optimized to one or the other way. And so drugs which do not show really per-oral absorption must not per se be unusable in this way. Yeah? But there are different possibilities for optimization and so on. And then when we go from absorption to going into the plasma, and that can be distributed into the different areas for the different points. Here we must see that this administration pathway strongly influences the increase of the concentration. Yeah? So when you give an IV application, that is more or less the fastest way to go into the plasma, and then you have some peaks there. If you go for an intramuscular application, then it is mostly separated from the muscle. And then you do not have these large peaks in the concentration and so on. So maybe it's then prolonged for a longer time, also with some other possibilities in the different ways. Yeah? So the different ways go then to gut, skin, muscle, cerebrospinal fluid if you put it directly into your brain, into the structure, or by inhalation into the lung, and then into the whole body distribution processes in this way. And then when we have this distribution, we must say that it always goes also to the liver, and we do have also here another system. It's by the biliary system, and there we have a responding system. So when you excrete your compound, after distribution, I'm not sure it's fully working this way, huh? After distribution in this way. I will take the other can also take the mic, the hand microphone. Yeah. So these compounds can also be absorbed in the gut, distributed in the plasma, and then it can be redistributed by the elimination into the gut because this is also our redistribution system. But then with the biliary system, it could be reabsorbed into a circle in this way, and thereby you prolong the circulation time in the body. So this biliary system here through the portal system can then prolong the activity of the compound, although it is well distributed and so on. And then with the after distribution, we do have the metabolization mostly by the liver, but also by many other cell systems and also directly in the plasma. And we do have the process of elimination. So in many cases, our kidney, the renal elimination are the most prominent one into the way, but you can also directly by feces go through the gut into this way. And we must also be aware that you can also sweat out your compounds. So by milk elimination or sweating, you can also get rid of the different compounds, and sometimes you can even smell the drug consumption by some people, or you can also expire this by exhaling, not only by inhaling, but also by exhaling in the different stuff. So many possibilities for elimination in this way. But I do not want to overcome the distribution process, because this is also important. With the distribution process, we have different compartments. So when you have here, for example, the intestinal water, then your compound could be what is here the yellow dots. This is the free drug. And the free drug can then have a good plasma binding. Plasma binding or other things then goes for the bound drug here into this way, and there you always have an equilibrium. The only thing here is that from one compartment to another compartment, you have a cell barrier. So the proteins binding to our compound do not pass the cell barrier, so only the unbound drug is passing the cell barrier, and thereby these free compounds are passing the cell barrier by different velocities and different on-off phases into the different areas. And then you have to be aware that there are different binding proteins here, so there are different possibilities in this compartment in which way this is really then bound and into the equilibrium into this is really bound. And there's also the possibility that the on-off phase, so the kinetics in which way this free compound is put into this fatty compartment or getting out of this fatty compartment, that they are different. And if you have a fast onset going into this compartment and you're having a low back distribution, so off phase into this area, then your compound would be get a much higher concentration in the fatty compartment because of the large onset and the low offset in these different compartments. So there are not only the bound and unbound compartment, but also the distribution time with the on and the offset for the different structures. And you can see here this multi-compartment model where we have the blood and the distribution partner, and we have different compartments like the lipids or the bones. And you can see here we have a fast onset and a very low offset in the structure, and so we have a higher concentration in this compartment. And then even with the bones, we do have from the lipid here also a fast onset and a low offset for the structure. So also there would be enrichment of this drug in the bones, for example. And this could be the clear. We do have a class of compound which are the aminophosphates, which have a poor absorption, but they have a very high distribution into the bones, where they are responsible for bone health in different aspects, and they do have sometimes a half-life of 3 years in the bone compartment because they are very slowly put off of these different compartments, and thereby the clearance rate here, the off rate of this different structure are quite important for the different structure. So absorption and distribution, quite important points for drug interactions. And then we go here for the metabolic studies in this way. Metabolic studies goes for different phases. We go in phase 1 and phase 2 in the metabolic study. Phase 1 means reaction where you do something directly on the molecule, like oxidation, reduction, or hydrolysis. And we do have a so-called phase 2 reaction, where you have a conjugation with body compartments, and mostly with glucuronic acid, sulfuric acid, acetic acid, different amino acid, or with methyl groups into the different possibilities. So you differentiate between the different structures in the way. And for the organic chemistry here, the metabolic pathways are mostly, not always, but mostly that the compounds get more hydrophilic. More hydrophilic means better renal application or renal elimination, and renal elimination means you get rid of this xenobiotic, of this potentially toxic compound into this pathway. These phase 1 and phase studies can be done in many different cells and different cell lines, but our main compartment in which way we have this metabolic enzymes are the liver. So liver is the main compartment where we do have the different structure, and also the liver structure is that is very rich in blood flow, and the cells are highly reachable by the blood ingredients in this way. Yeah? So then that can be done. And then we do have also this mitochondria in our cell lines to giving the energy for the metabolic process, which is really essential. And then we have the endoplasmatic reticulum or the Golgi apparatus, and the metabolites are then be taken into some granular or some liposomes in this way that do not toxify the liver cells, but they can be excreted then into the plasma after a certain way. So also the liver cell must be protected, and we know from different metabolic pathway where you produce reactive and highly toxic metabolites, that then the liver is early accessed by this toxic compounds, and then you have a liver injury in this way. So that's one of the important things in which way these things could be modified into the different aspects. So liver, one of the main aspects in this way. And then we have the different enzymes and enzymatic pathways for the different structures to go here into the structure. Cytochrome P450 are the most important pathway in this way for phase 1 studies, because these are oxidoreductases, and these monooxygenases, they can do a large number of different things in different aspects for the different structure. I do not want to go into detail. I will show you later on some details in which way this can be considered and will be considered into the pathway. But you see many different pathways are involved here with the cyclooxygenase and so on. Different CYP-related reactions can be induced into this way. I just want to show you one way in which way this really is important for different structures and different structure compartments. I think most of you know diazepam as Valium, the benzodiazepine as a highly effective sedative in the different structures. So this Valium has a GABA agonist in the different pathways, and leads to sedation, leads to reduction of the muscle tonus, and anxiety behavior. Yeah? So these three main factors are there. And then you can see that this diazepam is demethylated by a different structure, it can be hydroxylated. Both of these reactions are phase 1 reactions, because demethylation and oxidation is a phase 1 reaction, and then in the phase 2 reaction it is conjugated to glucuronic acid, and then this hydroxy group is conjugated to glucuronic acid, and then this could be easily eliminated into the different pathways. So phase 1 and phase 2 reaction very often go hand in hand in the different pathways and so on. Here it seems that these Valium, this diazepam, has been applied for many patients, and also especially for elder patients, because they cannot sleep very well, and then as a sleepiness pill this had been given, but had given the bad effect that when the elder people who had to stand up late in the evening, maybe go to the toilet or somewhere else, and then they do not get the correct muscle tonus, because this directly also is reducing your muscle tonus in this way, and thereby they have a higher range of falling down, of breaking bones and things like this. And thereby the long duration is not really wanted. And that means, that led to the finding that then this compound with the hydroxy group can be taken directly as an active metabolite, and this active metabolite has a much shorter half-life for a different structure, and with a shorter half-life this is much more applicable for the patients, because it can better apply and have better compatibility for the different structure. So sometimes even the metabolite investigation then leads to new drugs which have some advantage if you understand all of the different structures and so on. And even Valium here, this diazepam, this even is an active metabolite from midazolam. It's a very long-acting compound and goes for a number of different metabolites in this way. This is also the showing that we do not have only one metabolite. In most cases we have a number of different metabolites. And then you have to investigate all of the different metabolites in the different pathways and so on. This is the enzymatic reactions and so on. And when we have enzymes, then we have different substrates for the enzymes. And these different substrates, when we have different substrates at the same time, these different substrates lead to an inhibition. The inhibition then means that different substrate cannot be treated simultaneously for both of these things, and then we have to wait for this. Yeah? So that's one of the reasons we are going here for a different structural element and go here for the different aspect in this way. Yeah? What we are doing here is that we have different kinds of drug structures, and the different kind of drug structures, they are going as substrate, making a substrate as an inhibition, or as an inhibitor who is not substrate, who are transformed by other compounds in the different pathways, and then go for the different structural and structural elements in this pathway. Yeah? So that means that this will go for different effects in the aspects here, and then we have to investigate if our compounds as inhibitors are substrates or inhibitors without being substrate function for the different structures. So there are different possibilities in which way you can inhibit. Why is this important? Why do you think it's important to have a substrate or an inhibitor? Why it's important to differentiate between the both aspects in this area? Substrates, when you have two different substrates, then you have two different interactions because they are both metabolized by the same enzyme, and then you have a prolongation of one of the other compounds. The prolongation then is aber minimal, and then it could be modified into different aspects, and this prolongation means that one or the other compound who is a better binding structure could be more easly metabolized. When you have an inhibitor, then nothing is metabolized during this pathway, and then you have to work on this pathway for a longer time, and then this inhibitor means more interaction than the other. These substrate inhibitor variations means that you have a high possibility for drug-drug interactions. And then your drug interaction does not fulfill the pharmacokinetic criteria you have investigated, because you're investigating your compound only in mice as your compound and not into interaction with other compounds. But that is not the real way in which way this is interacting with the real world data. When you treat the patient is not only getting your only new compound, they are normally getting a number of different compounds, and thereby they must be investigated for the different structures. Yeah? And then we have to investigate here the phase 1 and phase 2 enzymes. They are responsible, and you see here cytochrome P45. Here, see here most two-thirds of all of the different reaction conditions, and then you have some hydroxylases, alcohol dehydrogenases, and so on, who do some other aspects. This clearly shows that the cytochrome P450 family is quite important for metabolic pathways. For the metabolic pathways, it's also important that they are not only important for metabolism, but they are also important for the synthesis of some natural compounds of hormones in your own body. So cytochrome is not only for the metabolic pathway of xenobiotics, it's also for the metabolic pathway of endogenous compounds in this way, and thereby you could also get some hormonal dysregulation by these compounds and other things you get also into these different aspects for the different structure. With the phase 2 reaction, you have different conjugation reaction, and there, for example, the glucuronidase transferases you have here, or some sulfotransferases you're having here, but you are seeing this is a little bit more diverse in this way. And at the end, you can see that this is more or less like an autobahn. Yeah? And you have different pathways, and then you can see here the cytochrome 3A4, for example, is a very big pathway you're having here, a very big autobahn where many compounds going through because of the high importance of these drugs. Then you can also see, then when you block this pathway, then this autobahn gets very crowded. Yeah? So there will be a traffic jam and nothing goes really there, and then if the compound can go another autobahn, if they also have some other pathways for metabolization, then there would be no problem. But if they only have this pathway, then you get into problems with this structural variation. So it's better to have more than one pathway for the metabolization, because for the interaction then, if you have only one pathway, then you get into problems with the different structural elements for the different pathways here, so on. Yeah? So the cytochrome P450 is the most important pathway here for the different structures and for the different pathways we are going on for the different structures in this way. This also depends then when we have to investigate this metabolic pathway and the metabolic possibilities. Yeah? So on the very first step, we identify the pharmacodynamics. Yeah? And when we have identified the pharmacodynamics with the different ligand binding site and different structures, and then we go into different interaction possibilities, into different modification for the different structures we can go on for the different elements here. And this means then we have to see in which way these assay can interfere with the different structures and then can go for the different elements. What we want to know also is the number of the different interactions we are going here, and you see here different possibilities for interaction and retrospective adverse drug reactions. And you see here two slides or two pills, one above 100 milligram and the other with lower points of lower dosages in these pathways. And you see the lower the dosage, the less pathway you are having here, the lower warnings you have, because when you have low compound warnings, then the possibility of active metabolites, of interactions are much lesser. So the more active your compound is, the better you have some possibilities for going there into drug interactions and or the larger compound you have, the larger you have the possibility for drug interactions into the different pathways here. Yeah? So then we go into elimination. Elimination is clearance, and clearance means Also, metabolization is a kind of elimination, because your drug is eliminated and you form some metabolites. And these metabolites may have some additional effects, more or less, into the different pathways for the different structural elements. Yeah? Yeah? I think I have to stop here, because I will make it later on, but I do have some stomach problems with me, and cannot, and I'm sorry I cannot proceed here. Sorry for this. Yeah, I sorry I have to stop here. Yeah, we can make it maybe this afternoon later. Yeah, and then maybe you can go interfere with this, but at the moment I think I'm not possible to proceed. Yeah. Okay. Sorry for this. Yeah. My stomach is not working.